That's going to move us into the second talk of this session, where we have Andrei Kovanov from Google, who's going to be diving down a bit further in the stack into the kernel itself. Andrei, if you'd like to share your screen.
Okay, thank you. So thank you for allowing me to present on Android Security Symposium, and welcome to my talk about memory tagging for the Linux kernel. So my name is Andrei. I am employed by Google, and I mostly work on different bug finding tools for the Linux kernel. Since some time ago, actually also started doing work that is related to security exploit mitigations. And this is where memory tagging actually comes in. And so the plan for today is, first of all, I'm going to introduce my team. I'm going to tell you about different kinds of tools that we have for user space and for the kernel. The next part is going to be about memory tagging itself. I'm going to explain the concept. I'm going to explain what is the current state of memory tagging in Linux and Android user space. And finally, the last part is going to be about the kernel. So my team actually consists of two parts. The first part works on user space, and there we have some bug finding tools like sanitizers. I think people who write C and C++ code have heard of them or have probably also used them. We have some tools that assist you with fuzzing, and one of the recent developments, we also have what's called Tag-Based which is a sampling-based memory bug detector. And the idea is that you can actually use it in production to find memory bugs that happen in production code while it's running. The user space part of the team also works on mitigations like CFI, shadow call stack, and some of the others, and of course, memory tagging. Today, I'm going to be expanding more on KASAN, which is hardware-assisted address sanitizer, and memory tagging itself, of course. So the second part of the team is where I work, and that part of the team actually works on kernel tools. For the kernel, we also have a set of sanitizers that allow you to find different kinds of bugs. I guess the oldest one is the address sanitizer that finds memory corruptions, and the newest one that was just merged into the mainline kernel a few months ago is KASAN, which finds data races. We have Syscaller, which is our coverage guided fuzzer, and right now we're also working on KFence, which is something like Tag-Based but for the kernel. So it's a sampling-based memory bug detector for production use. For mitigations in the kernel, first of all, we've been working on memory initialization, and with memory initialization, the idea is really simple. We want to initialize heap and stack memory to avoid leaking information from the kernel. And today I will mostly focus on a new KASAN mod, which is a software implementation of the memory tagging concept for the kernel, and it's called Tag-Based KASAN. So a typical point that's being made here is we do have a lot of software that's written in unsafe languages. And those unsafe languages allow you to do a lot of weird things. And as a result, you do get a lot of bugs and a lot of memory corruptions. As we know, some of the memory corruptions are exploitable. So instead of investing into fixing bugs, it makes sense to also invest into mitigation that will actually prevent those memory corruptions from being exploited. And one of the links that I have here is a link to our Sysbot dashboard. And Sysbot is an automation on top of Syscaller that essentially fuzzes the Linux kernel in the cloud. And currently we have almost 700 open bugs in the mainline Linux kernel. And the situation is not getting better in time. So memory tagging is one of it can be used as a security mitigation. And right now, let me explain you the concept. So the goal of memory tagging is to ensure that memory accesses are safe. The way this is done is by splitting the memory into memory granules, and each memory granule is associated with a tag, which is also sometimes called a color. Each pointer that points into memory also has an assigned tag. And the idea is to make sure that on every memory access, the tag on the pointer actually equals the tag on the memory. If they're not equal, then this raises an exception. And of course, depending on the implementation, you can have different sizes for memory granules. You can use different types of tags. Usually a tag is an integer, and the integer you're using some bits to store it. The way this is typically implemented is the allocator does the following allocation. First of all, it has to align the allocation up to the granule size, because we cannot use, like, this is the smallest granularity that we have. Then the allocator chooses a random tag or uses some other rules to choose a tag. Tags the allocated memory, tags the pointer, and returns the pointer. And of course, the pointer and the memory tagged with the same tag. On the allocation, we can retag the memory with a different tag. And then on memory access, what happens is that we actually check that the pointer tag is the same as the memory tag. So here's a small example. Let's say we are allocating k bytes, and n is our granularity. And let's just say that k is actually more than n, which means that it's not enough to have one granule to hold k bytes, but it's enough to have two. So this is how the memory is going to look like. And here, each cell actually represents a memory granule, and our p pointer actually starts with address 0, our object of k bytes. So here we can see that the p pointer is tagged with the green tag or green color, and the two memory granules that hold the object of k bytes are also tagged with green, and this is what the allocator did. The other objects that are on this picture are tagged with different colors. So now let's say we're accessing byte number to n. Byte number to n actually lies in the next granule, and it has the color purple. But since we're using the pointer p, which is tagged with green, and the memory is tagged with purple, green does not equal purple, and here we have an out of bounds. Similarly, for a use after free, what happens is that after we free memory, we retag the granules that belong to the object, and here we use the red tag. And when the access to the object happens, we have the pointer that is tagged as green, we have the memory that is tagged as red, and since the tags are not the same, we do detect a memory access violation. So if you actually look at this picture and think about it, what's going to happen if our out-of-bound access actually still in the same granule still in the second granule, but is accessing past the k bytes. So in that sense, that access is not going to be detected, and our bug detection with memory tagging is actually probabilistic. So here's an example. Let's say that our memory granule size is 16, and let's say we use 4 bits to store a tag, which means we have 16 different tag values. And let's allocate 35 bytes. And when we're going to be accessing byte number 40, byte number 40 is going to be actually falling within the third granule. So to hold 35 bytes, we need 3 granules of size 16. And byte number 40 is within the third granule. So in this case, this access will not be detected. If you're going to be actually accessing the next granule, the fourth granule with offset 64, there is still a chance, if the tags are assigned randomly, that the tag on the next granule will actually match the tag on our object. And the chance of this is if we're assigning tags randomly is 1 out of 16. Here we can actually make sure, so it's up to the implementation, but the implementation can make sure that objects that are next to each other in memory actually get different tags. In this case, for linear buffer overflows, we can actually make sure that memory tagging always detects them. But if we're accessing a very, very far out of bounds, let's say we're accessing 100, 500, then there is no way for us to make sure that the tags are different, and there is still a chance that the tag is going to be the same. And the same happens with use of the free. So let's say we freed the pointer, but that's someone else allocated object on this place, and someone else retagged the memory with a random tag. So in this case, there is still 1 out of 16 chance that the tag on the memory will be the same as we had before. So now this was the description on concept, and a particular implementation of memory tagging has to address the following questions. First of all, we have to choose a particular granule size. We have to decide how many different tags we have and how many bits do we use to store a tag. You have to figure out how to assign and store pointer tags and how to assign and store memory tags. And finally, something has to perform the actual comparison of tags. So one of those questions I'm going to actually answer right now, how pointer tags are stored, because all of the implementations we'll be discussing today are going to be using the same approach. And this approach relies on ARM top-byte ignore. ARM top-byte ignore is an ARM feature that allows you, when enabled, to ignore. So the CPU actually ignores the top 8 bits of any address it dereferences. And you can enable it with setting the TBI bits in the TCR register, and there is a separate bit for the user space, there is a separate bit for the kernel. And since the top byte of any pointer is going to be ignored, we can store any value in the top byte, right? And this way we can actually store the tag that's assigned to the pointer in the top byte. Of course, the limit that we have here, since we can only use 1 byte, is that we have 8 bits per tag. So we can only use 256 different tag values. There are a few memory tagging implementations that are either exist or are in development right now. And the first one is the Spark ADI. And this one I'm not going to be discussing, but it actually exists in some Spark CPUs. It's implemented in hardware, and they use 4-bit tags and memory granules of 64 bytes. The one that I'm going to discuss on the next slide in details is ARM memory tagging extension, and it's being developed by ARM. And finally, right now, we actually have a partially software implementation of the memory tagging concept as a hardware-assisted address sanitizer. I say partially software because it still relies on the top byte ignore, but luckily top byte ignore is present in a lot of modern ARM CPUs. And I'm not going to discuss hardware-assisted address sanitizer right now, because in the third part of the talk, I'm going to be discussing its implementation for the kernel. And let's concentrate on memory tagging for now. So ARM memory tagging extension has been added in ARM v8.5 not very long ago. And right now, it only exists as a spec, so there is no actual hardware yet. And with ARM memory tagging, we have granule size of 16. And we have 4-bit tags for memory and for pointers. And the 4-bit tag is actually stored in the top byte, so ARM memory tagging also relies on the top byte ignore. With ARM memory tagging extension, the load and store instructions, they will actually compare tags in hardware and make sure that the tag on the pointer matches the tag on the memory. And of course, we have new instructions to manipulate the tags, like set tag values and stuff like that. If you think about it, we have 2 different applications for MTE. And the first one is we can make better and faster debugging and testing tools. For example, right now we have a software implementation, KASAN, and we can actually change it to depend on MTE. It's still going to be a debugging tool, but instead of relying on software, it's going to be using the hardware, which is going to be faster. The same thing we can do for the kernel, and the same thing we can do for our sampling-based tools, for example. The second application is using MTE as a security mitigation, and it can be used in the kernel, it can be used in the user space. And I highly recommend looking at this paper by Microsoft, where they address, so they're trying to figure out what kind of exploitation techniques does memory tagging protect from. And yeah, there is also another interesting point that actually, when you have memory tagging, it turns out that you can, when you're setting the tag on the memory, you can initialize the memory at the same time without no extra cost. So you actually get memory tagging plus memory initialization for the same performance impact. And there is a link here you can follow and find out the details. So this is, let's say we're using memory tagging, or let's say we're using KASAN in user space, and we have a problem. The problem is that when we use top byte ignore, the pointers, the user space pointers, will end up with top byte set. But the Linux kernel by default does not expect that. The Linux kernel only accepts user pointers that have 0 in the top byte. So to address this issue, a tagged address API was developed. It took a long time to figure out, but right now it's in the mainline kernel and has been backported to Android kernels 4.14, 4.19, and 5.4, of course. So this is required for KASAN to work, and in the future will be required for MTE. And you can find out more details in the documentation link that I have here. But the general idea is that we just taught the kernel, we explained to the kernel that tagged user pointers are okay in certain cases. And here we come to the current state of MTE in user space. So first of all, for user space MTE, we do have the software implementation that works. And we do actually have an Android open source based image that includes user space apps built with KASAN. And you can just download the image and you can flash it onto your Android device. And this, of course, requires what I mentioned on the last slide, the tagged address API, but this has been merged into Android common kernels. The second thing that we have that will be required for proper user space MTE is more kernel support. And more kernel support is in progress. There are patches on the mailing list and is being discussed for mainline inclusion. It's not in mainline yet, and it's not in Android yet, but hopefully will be at some point. And finally, ARM actually has an emulator that you can try to use, and it has MTE available. Okay, now we come to the third part of the talk, which is about software tag-based KASAN. And initially it was called kernel KASAN, so we wanted to implement KASAN for the kernel. But at some point we decided to change the name to better integrate it with the current naming scheme that is used for KASAN. And so for those who don't know, KASAN is a memory bug detector for the Linux kernel. It can find out-of-bounds bugs on heap, stack, and globals, and it can find use after free bugs and some other types of issues, memory issues. It's really easy to use. The only thing that you need to do is to flip config KASAN when you build the kernel, and that's it. Just build the kernel and run it. This tool is really useful in case you want to detect memory corruptions. So let's say you have some memory corruption and you're trying to track it down, but the problem quite often is that memory corruptions actually crash your kernel or your program at some random points because the memory is corrupted. And KASAN tries to detect the corruption as early as possible, preferably at the point where the memory corruption occurred. So when it detects a memory corruption, it's going to print a report like this address was involved, this object was involved, here's the call trace, here was the object was allocated, here's when the object was freed in case it's a use after free, and all information like that. And it actually has a very moderate slowdown in memory overhead, so you can use it for testing, no problem. And with software tag-based KASAN, we just added another mode to KASAN that is based on hardware-assisted address sanitizer. So the original mode that is now called generic is based on user space ASAN, and the tag-based KASAN is based on user space KASAN. And the idea of the new name was, first of all, we rely on memory tagging, so that's why we called it tag-based. And the software part comes from the fact that this does not require any hardware implementation for memory tagging. It does it in software. In the future, we will hopefully have a hardware tag-based KASAN, which will actually use hardware implementation in the form of MTE. And tag-based KASAN can be enabled with config KASAN SW tags, and it's been merged into mainline over a year ago, and it's been backported into Android 4.14, 4.19, and of course it's included in 5.4 since it's after it was merged into mainline. It currently only works with Clang, so it's not supported in GCC. And the original KASAN mod that we had is now called generic, and the idea here is the original mode actually does not depend on any architecture, so it can be used for ARM, it can be used for ARM, x86, and other architectures. There is quite a list right now, actually. Okay, so if you remember when we were discussing memory tagging, for a particular memory tagging implementation, we need to answer these questions. So I'm going to explain to you how KASAN works and then present the answers to all of those questions. First of all, most of the sanitizers, I think even all of the sanitizers that we have, they actually consist of two parts. The first part is a compiler module that inserts instructions around each memory access, and those instructions actually there are the function calls or actual instructions to make sure that the memory access is valid. And we have the runtime part that implements the hooks that are inserted by the compiler that has some annotations for the allocator. For example, in case of tag-based KASAN, we will need to mark the memory as tagged, right? And it puts all of the things together to actually detect bugs. So with tag-based KASAN, to store tags, we use shadow memory. And shadow memory is just a region of memory that is reserved specifically for KASAN. We use 1 byte tag for each 16 bytes of memory. Since the native kernel pointers actually have FF in their top byte, we initialize all shadow memory with FF. And when it comes to tag values, we actually do have two reserved tag values that are not being used when random tags are being generated. The first one is FF, because it's a native kernel pointer tag, like native kernel pointer top byte. And the second one is invalid, which is FE, and we use it for memory that is definitely inaccessible. For example, KASAN actually stores metadata per each allocated object, and this metadata stores handles to stack traces, allocation and deallocation stack traces, and we mark that metadata with FE. And we also mark freed object with the invalid tag. So this is how the shadow memory looks like. It's just basically part of address space, and the whole kernel address space linearly maps onto shadow memory. Since each 16 bytes of kernel memory have 1 byte of shadow, we just divide address by 16 or shift it by 4 and add the offset to calculate the address of the shadow memory byte based on the address of the kernel memory. This is the way allocator annotations look like. So let's say we have a kmalloc. Kmalloc is a kernel function that actually allocates memory, one of them at least. And by default, it just returns a pointer. With tag-based KASAN, we actually have a call around the returned pointer, which is called here KASAN kmalloc. And that call is going to generate a random tag. It's going to tag the memory by setting the shadow memory. It's going to embed the generated tag into the top byte of the return pointer and return it. It also, of course, does other bookkeeping stuff like saving stack trace handles into the metadata and stuff like that. So since, and of course, also all of the objects are aligned to the granule size 16. And since all of the objects actually store metadata, we also have to increase the object size by the size of metadata. KASAN kfree, which is the annotation for the kfree function that frees memory, actually retags memory with the invalid tag. Here's a small example. In this case, I'm going to be using TBI to top byte ignore to show the tags. So let's say we're allocating 35 bytes with kmalloc, and let's say the random tag that kmalloc generated is 42. So the pointer has been tagged with 42 with green tag, and the top byte ignore says 42. And the object of size 35, when you allocate it in the kernel, it's going to use the kmalloc 64 cache. So 35 bytes actually requires 3 granules of size 16, and then there's going to be the 4th granule that is actually used to store KASAN metadata. And this is the way it's going to look in memory. And shadow memory will store the tag values for these memory granules. The 3 accessible memory granules are going to store the same value as the top byte of the pointer, which is 42. And the last granule is going to be marked with invalid as FE. And finally, when you free the memory is also retagged to invalid. And this is the way it looks in memory and in shadow memory. So let me answer the question that I've presented before. The granule size with tag-based KASAN is 16 bytes, like with MTE. We have 256 different tags, but 2 of those are reserved. We have 8 bits to store a tag. And the tag, software tag-based KASAN uses TBI to embed tags into pointers top byte, and the tags are assigned an allocator and stored in shadow memory. And finally, the comparisons are performed by the compiler, by the instruction that compiler inserts when compiling the kernel. Let's compare the overheads that we have for software tag-based KASAN and the old original generic mode of KASAN. The CPU overhead turned out to be almost the same, around 2x, but the memory overhead is completely different. First of all, when it comes to Kasan, memory overhead actually consists of a few parts. And the first part is actually slot memory usage overhead. And it comes from the fact that, first of all, we need to store metadata after the object, and then we have to also align the objects up to the granule size. And in case of generic Kasan, the overhead is actually 2x, but in case of tag-based Kasan, it's only 20%, which is extremely low. The second part that contributes to the memory overhead is the shadow memory. And with software tag-based Kasan, we have to use twice less shadow memory than with generic Kasan. And finally, tag-based Kasan does not require quarantine. Quarantine is a feature that generic Kasan uses to delay the reuse of memory and increase the chance of detecting use of the free. And software tag-based Kasan does not need it just by design. And putting all of this together, we come to the following conclusion that software tag-based Kasan is actually suitable for usage on actual testing devices. And we actually do that internally at Google. And yeah, something that I want to mention here is that if you get a device, we actually have an image, an Android image that has software tag-based Kasan for the kernel, and then Hwasan for the user space in the same image. And the device is usable. You can actually use it for day-to-day stuff, and it's perfect for testing. With the old generic Kasan, we actually had a problem since it required too much memory. Most of the time, it would make the device unusable. So currently what we have is the software implementation of memory tagging for the kernel in the form of software tag-based Kasan. Currently, it only covers the heap memory or the slab memory, how it's called in case of the kernel. And the first thing we would want to do is to add stack and global support for it as well, to be able to detect bugs in stack and globals. The stack is currently in progress, and globals will be addressed after that. The second part after finishing this would be to add a hardware mod for tag-based Kasan that is actually based on MTE, just to make it faster. And it's still going to be a debugging tool. And finally, the last step, which we will hopefully reach at some point, is to have the MTE implementation in the kernel and to have it usable as a production-grade mitigation technique. So this is the last part that is a call to action for people who actually write kernel code or for vendors who actually make Android devices. So first of all, please use Kasan for testing the kernel. And it's really easy to use, just flip the config and that's it. I realize that the testing story when it comes to the Linux kernel is complicated. So if you don't have any tests, any kernel tests, please make sure that device boots at least without any bug reports. The second 2 points are actually about using tag-based Kasan. And the 2 reasons that you want to do that, first of all, because tag-based Kasan is usable on testing devices. You can actually use it to find bugs that are not reproducible during testing, but are reproducible during the normal usage of a device. And we use it internally. And finally, a tag-based Kasan is a good way to prepare yourself for MTE because it's the software implementation of the same concept, right? So you can try it and try to find out whether your kernel code has any compatibilities with it or whether your private drivers have some issues. And this will definitely simplify the future integration of in-kernel MTE. So this is the slides that I have. Thank you.
Wonderful, thank you. So we've got some time for questions. If we have anyone, I'm keeping an eye on both Mattermost and the Zoom chat, or if you want to raise your hand in Zoom. Renee, you're welcome to ask your question.
Thanks, Andre, for the excellent talk on introducing not only that specific KASAN version, but the whole topic of memory tagging, which I think maybe may have been new to some developers, but is something that most of us will have to deal with in the near future. Now, what I was wondering is if you already, if syscaller was now already able to find more kernel bugs by enabling KASAN in your kernel test cases, and if so, how does the Linux upstream kernel community react to another flurry of syscaller bugs coming in?
Okay, I see. So syscaller, actually, initially, we've developed the first version of KASAN, the generic KASAN, before we had syscaller. So from the very first moment of using syscaller, we actually had KASAN enabled on syscaller. And with tag-based KASAN, we do not currently have an instance that is running on sysbot in the cloud, because we do not have proper setup for fuzzing ARM kernels in the cloud yet. Actually, if you start using tag-based KASAN for fuzzing with syscaller, I am not sure you're going to get many new bugs, because tag-based KASAN will not find like new types of issues in terms of memory safety. It might find new issues in terms of incompatibilities with using top byte ignore, for example. But the bugs, the memory safety issues for generic KASAN and tag-based KASAN are the same classes of issues. And since tag-based KASAN is actually a little bit weaker than generic KASAN, because the generic KASAN has more capability of detecting really small out-of-bounds accesses. So the main use case for tag-based KASAN is not actually fuzzing. I mean, it can actually be really useful for fuzzing on actual Android devices if you ever do that, because generic KASAN can make the device really slow and unusable, and tag-based KASAN should allow the device to keep up. So you can use it for fuzzing on devices. But for fuzzing in the cloud, I don't think it's going to be very useful.
Thanks for clarifying.
So as other folks are thinking of potential questions, so again, thank you for the great overview of the topic. It's an area that I'm not particularly familiar with, and I learned a lot throughout the talk. You know, one of the things that you mentioned was there's slowly becoming more and more hardware support for doing these tests. As this hardware support becomes more widely available, do you see potential for these techniques to possibly be used more generally as a runtime defense, or is this always going to be a testing sort of capability?
Yeah, so my hope is that eventually we will have, in particular, memory tagging be used as a mitigation and not only for testing. It's like the ultimate goal is to actually have it to be used as a mitigation. So
in that context, then, one of the early slides you had talking about how the tagging works and the limitations of what you can actually put in the tag size, it became somewhat probabilistic. Am I right?
Correct.
So if you think about, you know, probabilistic defenses, of course, are useful, right? ASLR is tremendously useful, but there are ways of getting around ASLR by just trying lots and lots of times. Do you see similar sorts of issues here, or is it the fact that this would be in the kernel make it less so because it's not scalable to try as many times as you would need?
Yes, so there are, of course, the probabilistic nature of MTE makes it possible to bypass in certain cases. And the initial version that we will have will probably, be vulnerable to those. And okay, I'm going to split it into parts. First of all, about the probabilistic nature. So there are some modifications that you can do to memory tagging to make sure that certain bug classes are detected with 100% probability. For example, what I've mentioned with assigning different tags to memory objects that are next to each other in memory. And you can just make sure that the tags are different. For example, you can keep generating a new random tag until you get a tag that is different from the ones that are around those, right? For use of the freeze, there is actually a discussion right now. It's mostly being discussed for user space MTE. I'm not sure if this will be applicable to the kernel. It's about, so those who are interested, you can search for a mark us paper. It's called like mark us. And so I'm not going to go into details, but the idea is that there is an approach that will actually allow you to detect use of the freeze with something very, very close to 100% probability, maybe even 100%, and without any additional impact. And when it comes to the kernel, actually bypassing MTE when exploiting a bug will be, when we have MTE, will be a very interesting topic for research. And in kernel work, of course, have less flexibility in terms of that we cannot retry to exploit a particular box 100 times, because the first time kernel crashes, it's just going to crash. It's not a user space process, a user space daemon that will just be restarted, right? So in this case, attacking the kernel is harder. And what I remember is that one of the talks of Jan Horn, who is a Project Zero security researcher that works on Linux kernel, he actually mentioned that a particular way that a user might be able to extract tags from the kernel, and by using a particular syscall that allows you to predict whether two regions of memory actually have the same tag. So there are going to be attacks like that for sure. And the probabilistic nature of MTE, of course, makes it not 100%, not 100% protection from everything. But my understanding, based on my experiences writing kernel exploits, is that this is going to make writing kernel exploits an order of magnitude harder, or maybe even more.
That's awesome. So we've got a question on Mattermost, kind of two-part question. The first part might be the conference organizers, but whether or not the slides will be available.
Yes, I will publish them on Twitter in like 10 minutes after the end.
Great. And then the second question, which you touched on a little bit kind of informally, but I think the question is a bit more specific. Martin's asking what the expected overhead for hardware implementation is on a mobile device.
Yeah, it's a good question. Before we have the actual hardware implementation, no one knows yet, but the expectation is to have it in, like, it's usually been expressed as a single-digit % impact, something like this. So it's less than 10%.
Okay. All right, well, excellent talk, and thank you for all of the answers to the questions. I think that concludes, well, first, virtual round of applause for Andre, wonderful talk.